Today, I'll be sharing my Engineering Mechanics 213 Honors Option project, which focused on an applied approach to material identification. In this lab-based project, I obtained unknown material samples and conducted tensile tests to analyze the mechanical properties to then draw meaningful conclusions. Through this presentation, I will focus on the steps I took to determine the materials of the samples I gathered. I'll first discuss how and why I create a bone structure for my different samples. Then I'll move on to how I gathered the necessary data of the samples to determine the mechanical properties. Lastly, I'll discuss how I analyzed the data of the different tests to determine what the material was of the different samples. When I first gathered my different samples, they were rectangular and I couldn't just put that shape in the tensile tester because then there was a probability that the sample would fail in the grips and we wouldn't know if the break was caused by the material reaching its max tensile force or if the break was caused by improper loading or a pre-existing defect in the material. By having that bone shape in the picture shown, we can see the sample has a shoulder at each end and a gauge section in between. The shoulders are wider than the gauge section, which causes a stress concentration to occur in the middle when the sample is loaded with a tensile force. This stress concentration ensures a higher probability that the sample will rupture away from the ends. When the rupture of the sample occurs in the midsection, it is attributed to the material reaching its maximum tensile strength. The samples shown in the picture are the samples I used for my project. However, I had to use the machines in the learning factory to cut them down into that bone structure you see. From the learning factory, I used the metal shop mills to accurately cut the metal samples into the bone structure. Then for the wood sample, I went to the learning factory's wood shop and used their bandsaw. This bandsaw, while not as accurate as the mill, still allowed me to cut the wood sample at different angles to create the bone structure. Once the bone samples were done, I now had to take them to the tensile tester. The reason I used a tensile tester is because the tensile tester allows me to assess the material's tensile strength, yield strength, and other important material properties. The way this machine works is by placing the sample into two clamps, as seen in the picture here, making sure the sample is placed perpendicular to the clamps. The top clamp then moves up slowly, increasing the normal force exerted onto the sample, while also measuring the change in distance between the clamps. This method allowed me to get the force applied to the load as well as the change in distance over time of the material. However, there is a more accurate method to finding the change in distance of the material, and that is to use the extensiometer. It is attached to the material like shown in the picture, and as the material is pulled apart, the extensiometer follows the extension of the sample, allowing for a more accurate measurement of the change in distance over time of the sample. The data received from the tensile testing of the samples gives the force applied to the sample over time as well as the change in distance of the sample over time. From these data points, we can determine the stress and strain of the material. By first finding the cross-sectional area of each sample, making sure it is the area of the middle section of the bone sample, I divide the normal force given by the tensile tester by the cross-sectional area to find the stress. Then by using the change in length given by the extensiometer data and dividing it by the gauge length, which is 1 inch, I can get the strain. However, the extensiometer can only extend a certain amount. So after a certain point, to get the strain, I have to use the change in distance given by the grips over time divided by the initial distance and the distance between the grips. By doing this, we can get the stress and strain over time of each sample. For sample 1, the cross-sectional area was 0.0625 inches, and when doing the tensile test for this material, it broke very close to the grip, and this was most likely because of a small imperfection at that point. By determining the stress and strain over time of the first sample, this stress over strain curve can be created, allowing us to find the different mechanical properties of the sample. For the graph, you'll notice there aren't a lot of data points given, and that is because when doing the tensile test, the grips moved at a very fast pace, so not a lot of data was able to be retrieved from the test. The pink points on the curve represents the points where I had to use the change in distance given by the grips instead of the extensiometer to finish the curve. The strain from those data points may be inaccurate as I had not measured the distance between the grips initially. So to estimate the initial length, I used the gauge length of my sample dimensions, where the smallest area would be. From the stress strain curve, I was able to determine the tensile strength, which is the point where the stress reached its maximum values. I also determined the yield strength by drawing a line parallel to the linear portion at the beginning of the graph, with an x-intercept of 0.02. And the point where the line intersects the curve is the yield strength. On this curve, the yield strength was approximately 35.7 ksi, and the tensile strength was 37.5 ksi. The last property I found was the modulus of elasticity, which can be found by finding the slope of the linear portion of the curve. This sample's modulus of elasticity was 10 times 10 to the power of 6 psi. Based on these values, according to Engineering Toolbox aluminum alloy's mechanical properties, this material is most likely aluminum 6062 with a temper of 6, as this material's properties has a modulus of elasticity of 10 times 10 to the 6 psi, a yield strength of 35 ksi, and a tensile strength of 38 ksi. All these values align very closely with the values I found experimentally, as the modulus of elasticity is the same. The percent error between the yield strength is only 2%, and the tensile strength is only 1.3%. It is ideal to have a percent error of less than 5%, since it shows that actual values are accurate. For sample 2, the cross-sectional area was 0.0625 inches, and when doing the tensile test for this material, the speed of the tensile tester was adjusted, allowing for more data points to be acquired. The pink point on this curve is the same as before. It represents the points where I had to use the change in distance given by the grips instead of the extensiometer to finish the curve. This curve, the yield strength was approximately 37.9 ksi, and the tensile strength was 41 ksi. Then finding the slope of the linear portion of the curve, this sample's modulus of elasticity was 10 times 10 to the 6 psi. Based on these values, according to Engineering Toolbox aluminum alloy's mechanical properties, this material most likely is aluminum 6151 with a temper of 6, as this material's properties has a modulus of elasticity of 10.1 times 10 to the 6 psi, a yield strength of 37 ksi, and a tensile strength of 44 ksi. All these values align very closely with the values I found experimentally, as the modulus of elasticity has a percent error of 1%, and the yield strength has a percent error of 2.43%, and the tensile strength is 6.82%. It is ideal to have a percent error of less than 5%, since it shows that actual values are accurate. However, even though the tensile strength percent error is above 5%, it is still below 10%, showing the value is still precise. For sample 3, I was unable to gather proper data to determine the material properties, because the sample kept slipping the grips. Looking closely at the picture on the right, the grips shear the material off, causing the sample to slip without allowing for proper data to be collected. Because of this grip slip, that is what caused the data to be so skewed. From the previous two samples, we saw the stress-strain curve to have a linear portion first, then a negative quadratic curve. This curve is simply just linear, and even the data on this curve is not reliable, as I discussed earlier. Therefore, this wood sample is undeterminable. If I were to redo the sample, I would have to make sure the sample stays in the grip to get accurate data. Throughout this presentation, I focused on how I determine the material properties of my samples through tensile testing and determine their material. Thank you for listening to my presentation.